Warning. The Ocean Conveyor Belt is already collapsing. The storm came in sideways, salt spray freezing on traffic lights, power lines singing, and somewhere in the dark, a transformer blew like a gunshot. In a row house near Dublin, Maeve stuffed towels under the door as her breath fogged the air. The thermometer on her phone read -8. The forecast said again, unusual. The radio said, record breaking. Her phone buzzed. School closed, roads closed, neighbor group chat asking who had spare heaters. She whispered, not again. If you felt winter getting weirder while headlines say hottest year, this is the link. The Ocean Conveyor Belt isn't a metaphor, it's a heat engine, and multiple lines of evidence suggest it's slipping. Roadmap of revelations. Here's where we're going. First, we'll meet the hidden engine that quietly ferries heat, north and cold south, day after day, century after century. It's called the Atlantic Meridional Overturning Circulation, the AMOC, and it behaves less like a dimmer and more like a switch, because fresh water pouring off Greenland and out of the Arctic acts like a kill switch you don't want to touch. We'll lay out the tripwires, the real-world signals already flickering. There's the stubborn coal patch south of Greenland in a warming ocean. Then we'll put that engine under stress. There are measures of the Gulf Stream's muscle that show it softening, and there's a statistical pulse hiding in noisy data, the telltale slowing heartbeat systems show before they tip. Meanwhile, we'll answer a hard question. Why did models long downplay how fast this could go? We'll get into resolution limits and blind spots, but also the new, sharper tools that change minds. Then we map consequences. Europe's winters shift colder and stormier even as the globe warms. Tropical rain belts slide. Monsoons stumble. Crops miss their windows. Fisheries move or fade as nutrient highways rearrange. Supply chains feel it in ports and insurance markets feel it in losses. Concrete stakes, higher heating bills, volatile food prices, coastal flood premiums climbing, mortgage risk in flood zones. This is not distant. We'll put faces to it. A Greenland harbor emptied of ice fish. A British farmer staring at a frozen field in April. A West African village built on the assumption that the rains arrive by June. Finally, we'll talk timing. The old line said, centuries. Recent evidence places meaningful risk within decades. And if the threshold is crossed, the flip itself can run on a human timescale. Months to years. Stay for the early warning hiding in plain sight. We'll need it. 1. Meet the machine. What the AMOC actually does. Before the diagram, stand on a winter ferry deck in the North Atlantic. Your cheeks sting, your gloves ice over, and the wind tastes metallic. The ocean is breathing heat into the air you're sucking in. Right then, right there. That warmth didn't appear by magic. A hidden engine dragged it thousands of kilometers north and is handing it to the sky above you, like a quiet furnace under the weather. That engine is already running weaker than it used to. This isn't a geology class timescale, it's a grit bill timescale. Start at the surface of the tropical Atlantic where the sun is relentless and the wind is steady. Warm, salty water peels northward along invisible lanes. As it travels, some of that water evaporates. The salt stays. The surface gets saltier, denser. By the time it reaches the subpolar North Atlantic, south of Greenland, around Iceland, the air above is cold and dry, especially in winter. The ocean coughs heat into the sky. The water cools, grows heavier, and begins to sink. Sinking isn't a metaphor here. In certain regions, water columns overturn like an escalator running in reverse. Dense water dives 2-3 kilometers down and flows south in the deep, a slow river beneath the surface. That's the overturning. The return path eventually loops around the tip of Africa, meets currents from the Southern Ocean, and after long detours and upwelling, finds its way back to the surface. It's a global loop, but the Atlantic is the loudest part of the heartbeat. Why does this matter for people? Because that northbound surface stream ferries about 1 quadrillion watts of heat toward Europe. It doesn't warm Paris by itself. The winds and the jet stream do plenty, but it sets the background state. With this heat shipment, winters in Northwest Europe are milder than they'd otherwise be at those latitudes. Storm tracks and the position of the jet stream lean on the temperature patterns the AMOC helps maintain. Farmers plan around spring thaw. Energy systems assume certain winter loads. Airports expect certain crosswinds. All of it borrows stability from this ocean engine. Salt is the quiet co-star. Evaporation pulls fresh water into the sky and leaves salt behind, boosting density. Cooling at the surface boosts density again. That pairing, salinity and temperature, decides whether water will sink. Change the recipe, and you change the sink. If the surface freshens, the water can stay buoyant even when cooled. If it doesn't, shed heat efficiently to the air, because a fresh, stratified lid blocks mixing. Deep water formation stutters. The AMOC also nudges the planet's rain belts. Shift heat in the Atlantic and you move the equatorial band where air rises and clouds burst, the intertropical convergence zone. That ripple reaches the Amazon's moisture supply and West Africa's monsoon. It ties into hurricane formation zones and the behavior of extratropical cyclones riding the North Atlantic storm highway. What happens between Newfoundland and Iceland doesn't stay there. Now the gut punch. This isn't a gentle slider you nudge a notch and watch it settle. It behaves like a switch. The AMOC shows hysteresis, multiple stable states under the same external conditions, depending on its history. Push with enough fresh water and it can snap to a weaker mode or a collapsed one. Ease off later and it doesn't snap back. The path down and the path up are not the same. That asymmetry is why this matters to your next decade, not your great-great-grandkids. You can flick it off far easier than you can flick it back on. There's a reason scientists still argue about the details. The ocean is messy, winds shove currents around, eddies, spinning features the size of cities, shuffle heat and salt. Some of the sinking happens in narrow straits and on continental shelves that global models have traditionally blurred. But the broad strokes are clear. Warm, salty water goes north. Cold, dense water goes south below. The exchange moves a massive amount of heat, and the balance rests on not diluting the northern mixing zones with too much fresh water. Think of a kitchen, sink with the drain half clogged. Water still goes down, but slower. Now you start adding soap until foam builds up. The foam is light and insulates. Suddenly the drain chokes, not because the pipe changed, but because the surface layer did. For the AMOC, the soap is fresh water from melt and rain. The foam is stratification, that layered ocean where the top refuses to mix with the cold below. When that lid clamps down over the Labrador Sea and parts of the Nordic seas, the deep engine hesitates. Meanwhile, the atmosphere adjusts fast. As the subpolar ocean hands over less heat, the sea surface pattern changes, cooler south of Greenland relative to the surroundings. Pressure fields reshuffle. The jet stream shifts and blocks. Europe gets longer winter cold spells, while the planet as a whole keeps warming. That paradox isn't theoretical. It's the same pattern showing up in recent winters and reanalyses. Trace the heat paths and the headline makes sense. And downstream, the deep return flow slackens. That affects sea level along the U.S. East Coast, because a strong AMOC pulls water mass and lowers relative sea level by altering the pressure gradient. Weaken it, and the gradient relaxes, water piles up a bit against the shore. Add storms to that, and you feel it in basements and insurance premiums. This machine runs quietly, with no on-off switch labeled in bright paint. But it has thresholds built into the physics, density differences, mixing rates, the geography of basins and sills. Cross those, and the mode changes. The unsettling part is that nature has done this before, abruptly, when a big freshwater pulse hit the North Atlantic. We'll go there next. 2. The kill switch. Freshwater from melting ice. To see the finger on the switch, look north. Greenland in summer sounds like rain hitting metal, but it's meltwater punching through ice. Rivers form on top of the ice sheet, dive into blue shafts, and blast out at the coast. That water is cold and fresh. It pours into the Labrador Sea and the Erminger Sea, right where the AMOC wants dense, salty water to sink. Add the Arctic to that. Sea ice that used to freeze hard and thick now shatters earlier, and when it melts, it leaves a fresh sheen across the surface. Fresh doesn't mix like salt. It floats and it insulates. Put enough of it over the North Atlantic and you build a lid. The ocean still tries to shed heat to the winter air, but the exchange slows. The top layer stays lighter, stubborn. Below, the water holds on to warmth. The overturning engine needs cold, salty surface water to fall. Instead, it sees a cap. Sinking falters. It's not just ice. Big rivers are shifting their loads. A warmer atmosphere drags more moisture out of the tropics and wrings it out at higher latitudes. Storms deliver heavier rain to the subpolar Atlantic, sweetening the mix further. In the Nordic seas and along the Greenland-Scotland ridge, the delicate balance that feeds deep water formation tilts toward buoyancy. Stratification thickens. That's the lid snapping tighter. We've seen what a pulse can do. At the end of the last ice age, a lake's worth of fresh water rushed from the Laurentide ice sheet into the North Atlantic. The climate flipped in the Younger Dryas. Europe plunged into cold within a human lifetime. That was a bigger slug of water than we're adding today, and the geometry of the Ice Age Atlantic was different. But the lesson is blunt. If you lower salinity enough in the wrong place, the overturning can stall fast. Modern instruments don't tell a simple story at one spot, but zoom out and patterns line up. South of Greenland, sea surface salinity has dipped over recent decades in key formation regions. The Labrador Sea, the Erminger Sea, parts of the Nordic seas. Argo floats feel the stratification, warmer layers trapped beneath fresher caps. Meanwhile, satellites that weigh Earth's gravity field like Grace and Grace Foe show mass draining from Greenland year after year. That fresh water has to go somewhere, and it shows up at the surface. There's a quiet accelerator in this mix. Several of Greenland's big glaciers don't end on land. They end in the sea. Beneath their floating tongues, Atlantic water has been sneaking in. Water a degree or two warmer than it used to be at depth. That warmth melts ice from below, thins the tongues, speeds the glaciers, and sends more ice and meltwater into the fjords. The more fresh water that exits, the more the local ocean stratifies. The more stratified it becomes, the less winter can vent heat upward. That allows the subsurface Atlantic water to stay warm and keep eroding the ice. It's a feedback loop, and it feeds the kill switch. Add another lever: wind. The subpolar gyre, the vast swirl south of Greenland, breathes in and out as atmospheric patterns change. When winds spin it into a tighter, more retentive state, it can trap fresh water, corral it over the very basins that need to be salty to sink. Those years, deep convection weakens. When the gyre relaxes, the cap can spread and thin. On top of the long-term freshening trend, these wind-driven pulses act like taps opening and closing over the mixing zones. Each factor alone is manageable. Together, they push a system with memory toward a threshold. And because this is a basin-scale machine, the signs don't flash like a red light on a dashboard. They appear as a cool patch in a warming map, a cold blob south of Greenland, where less warm water is arriving at the surface. They appear as a subtle rising of sea level along the U.S. East Coast, consistent with a slackening deep return. They appear as an ocean taking longer to heal from winter storms that used to mix it clear. None of this is distant in time. Freshwater input from Greenland has increased markedly since the 1990s. Arctic sea ice has lost more than half its summer extent since the late 1970s, changing how and where freshwater enters the Atlantic gates. Precipitation maps show the subpolar region getting wetter in winter. Observations and reanalyses point to stronger surface stratification trends, where it hurts overturning most. The picture isn't perfect. Local salinity can spike or dip from one year to the next. A harsh winter can tear open patches and spark deep convection again, briefly. But the baseline is moving. The cap is thicker, the deep is warmer, and the places where heavy water used to fall like stones are sputtering more often. So if you're looking for the finger on the switch, it's a hand, ice sheets, sea ice, rain, rivers, winds, and subsurface heat working together. The question now isn't whether they matter, it's whether the engine is already stalling in ways we can diagnose in time. The early signs are out there. The next step is to read them. 3. The 3 tripwires, signals of destabilization. Start with what you can see from space. Today, not in a simulation. In a world map of warming seas, there's a stubborn blue bruise south of Greenland, the cold blob. It shows up in NOAA, Hadley, ERA datasets. It shows up in the latest anomaly maps you can pull up on your phone right now. Everywhere else runs warmer over the last century, but that patch cools relative to its surroundings. It's not magic, it's a missing delivery. Less warm water is reaching the surface there. That's the first tripwire, a fingerprint. Many studies associate with a weakening AMOC, the same dipole pattern that pairs subpolar cooling with a warmer stripe along the shifted Gulf Stream. You don't need to trust any one model to notice the anomaly. It's lodged in observation maps year after year, and in recent winters it has intensified against record-breaking global ocean heat. Make it concrete. Airlines reroute around turbulence bands that set up along sharper temperature contrasts near that patch. Fishermen out of Newfoundland talk about green water lines where the temperature drops and fog clings a day too long. Weather desks in Europe watch that blue oval like a pressure cooker valve because it sets the tone for downstream blocking. This isn't a contour plot curiosity. It's a live feature nudging the weather you step into. Why does that matter to people? Because that patch isn't just a color on a chart. It's the sign of less ocean heat released into the atmosphere where European weather is forged. Shift that background field and you tug on pressure patterns, storm paths, and the seasons people rely on. That cold patch is a quiet, persistent note played under winter forecasts, and it keeps getting louder. Now pan from satellites to sea level along the U.S. East Coast. Again now. Tide gauges from Norfolk to New York tell a story of water creeping higher, faster than global averages at times. Nuisance floods have multiplied within a single career for harbor masters. Part of that is ice melt and thermal expansion, but part of it is dynamic. When the deep southbound limb of the AMOC slackens, the north-south pressure gradient across the Atlantic eases, and water stacks up against the coast. Think of it as a barometer for the Atlantic's muscle. That's Tripwire 2's cousin, because the same physics show up in another metric, the sea surface height and density gradient across the Gulf Stream. Oceanographers watch the tilt of the sea surface across the current and the shear of velocity beneath. When the Gulf Stream weakens, the slope flattens a touch and coastal sea level nudges up. Long records stitched from altimetry, tide gauges, and hydrography suggest episodes of weakening over recent decades, consistent with a gentler AMOC. Meanwhile, moorings strung across the Atlantic at 26.5 degrees north, the Rapid Array, have tracked notable year-to-year swings and a long-term decline from the early 2000s baseline. It's not a straight line, and it's not decades long yet, but paired with indirect proxies, it adds weight. And it's happening in the only sustained direct observing line we have. About those proxies. We can't put a flow meter on the entire overturning for the last 100 years, so scientists use fingerprints that physics predicts. The cold blob is one, the gradient across the current is another. There are also density reconstructions from the subpolar North Atlantic, sediment records that reflect past deep current strength, and the growth bands of corals that preserve changes in water mass properties. Different archives, different methods, same direction. The AMOC today is likely weaker than at any point in centuries, perhaps a millennium. Each line has caveats. Together, they form a picture you can't wave away with a single counterexample. Now for the third tripwire, the one that hides in noise but is flashing in real data sets. As complex systems approach a tipping point, they tend to recover more slowly from small nudges. Statistically, that shows up as critical slowing down, rising autocorrelation, and rising variance in time series that track the system's state. In plain terms, the system's wobbles last longer and grow larger because it's losing its restoring force. Researchers have applied these early warning indicators to AMOC-sensitive fingerprints, including reconstructed temperature and salinity contrasts across the Atlantic. They report trends in those indicators consistent with decreased resilience, and some studies go further, estimating a mid-century window for a tipping event under current forcing. That's a bold claim, so let's be clear about what's measured and what's inferred. We do not have a century-long direct measurement of the AMOC's full strength. Moorings like rapid date to the 2000s. The Gulf Stream itself is just one part of the overturning, not the whole. Sea surface temperatures can be pushed around by winds and aerosols as well as currents. Early warning statistics can be fooled by the choice of window or by unrelated variability. Those are real limitations. But here's why the inference remains strong and urgent. The cold blob persists across methods and data sets and lines up with known dynamics of reduced heat import. The sea level and gradient signals have the right sign and appear alongside independent evidence of subpolar freshening and increased stratification where deep water forms. The moorings see variability that matches wind-driven changes, but also a background easing. Paleoclimate analogs show the AMOC has two distinct modes and can jump. And the early warning metrics aren't alone. A newer, physics-based indicator looks at the freshwater transport at the southern boundary of the Atlantic. In models that actually tip, that transport passes a minimum on the way to collapse. Reanalyses hint the real ocean may be moving in that direction, and that's a real-time budget, not a vibe. Bring those threads together, and you get 3 alarms you can watch today. A visible fingerprint on the sea surface, a mechanical slackening registered in gradients and coastal water levels, and a statistical heartbeat that's slowing. Add cross-checks, sediment drifts that thin when deep currents weaken, coral geochemistry that records water mass shifts, isotope patterns that track past overturning changes. None of these alone proves a countdown. Together, they say the system is losing stability.
Now, what nobody knew in the 1990s was how fast a modern shove could matter. Aerosols, for example, once masked warming over the North Atlantic and may have muddied earlier signals. As those aerosols declined, greenhouse forcing stood out, and the structure of the ocean began to wear its stress more plainly. Freshwater input ramped, stratification grew. The tripwires started to glow, and they haven't dimmed. So the question becomes, if these alarms are real, where does the road bend? Past a threshold, the approach can take decades, but the transition itself, the flip, can compress into months or a few years. We're not waiting for future instruments or future models to tell us whether to care. The instruments we have already show direction. We need to talk about how slow pressure yields sudden change, why the path back is harder, and what that means for lives arranged around assumptions of gradual shifts. That's where we're heading next. Tipping points. How a gradual push becomes a sudden flip. Think of the AMOC as a ball resting in a shallow hollow on a hillside, but put your hands on it. Feel how it settles after a nudge because the hollow cups it. Now imagine a slow, invisible jack beneath the hollow. That jack is fresh water. Each year it lifts a millimeter. You don't notice at first. The ball still rolls back after pushes. The lip still holds. Then one winter, the jack is lifted enough that the lip isn't a lip, it's a line. A storm pattern tilts the board. Deep convection sputters in the key basins, and the ball kisses the edge. There's a split second when it could stay, then it tips. Gravity takes the rest. It doesn't clatter back into the old cradle, it drops into the next one down, and your hands can't stop it. Here's the physics behind that picture. Freshening reduces surface density, so winter cooling has to work harder to make water heavy enough to sink. While sinking weakens, less cold water drains from the surface, and more heat stays trapped below the fresh cap. That subsurface warming further stabilizes the water column. Warm water under cold is a loaded spring, reducing mixing and sinking even more. Meanwhile, with less heat delivered north, the subpolar surface cools relative to the subtropics, sharpening the temperature gradient that drives winds. Those winds can spin the subpolar gyre tighter, corralling even more fresh water over the sinking zones. That's a feedback stack. Each notch of weakening sets up the next, so the next nudge bites harder. Multiple stable states fall out of those feedbacks. One mode has strong overturning, salty subpolar seas, and robust winter convection punching to depth. Another has a much weaker or collapsed overturning, fresher subpolar surfaces, and shallow or intermittent convection. The same CO2 level can support either state depending on how the system got there. That's hysteresis in plain language. Path matters. Push the system over the rim with enough fresh water and it snaps to the weak mode. Ease off later and it doesn't snap back. You have to back away far beyond the original line, reduce the forcing well below the point where it flipped to climb out of the lower hollow. That's not stubbornness, it's built into the physics. Models test this with hosing experiments, adding fresh water to the North Atlantic at controlled rates. Many find clear thresholds, push beyond them, and the AMOC plunges to a low state. Stop the hose and it stays down. Only after removing far more fresh water than you added, or cooling the climate enough to resharpen density contrasts, does it climb back. The exact liter per second at which models tip varies, but the geometry of the response, two basins of attraction with a ridge between them, keeps showing up. In higher resolution setups that better capture narrow sinks and swirling eddies, the threshold shifts, but the basic landscape remains. The ridge is real, where it lies is the detail. Time behaves oddly around a tipping point. The approach can be slow because the system absorbs stress. You get years when deep convection returns, headlines calm, and it seems like a false alarm. But the restoring force is fading. Recovery from each perturbation grows more sluggish. Then a sequence of winters lines up. Fresh cap thick, gyre tight, storms less able to crack the lid, and the remaining pathway for sinking constricts. The change in the overturning strength during the actual transition can be steep, months to a couple of years in models that resolve key processes. Recovery, by contrast, is glacial, because the weak state reorganizes the whole basin and the feedbacks that hold it.
Once you're in the lower hollow, the walls are higher and slick with feedbacks. This is why we'll adapt gradually is a risky bet. Many impacts of climate change scale with temperature in a way that planners, at least in theory, can track. A tipping circulation doesn't. It rearranges baselines. Europe's energy system, sized for milder winters, suddenly face sustained cold loads and new storm patterns. Rain belts shift, and farmers who spent a decade adjusting to earlier springs confront colder, wetter ones. Fisheries that migrated slowly north don't just keep moving. The plankton communities beneath them reorganize as nutrient pathways change. Insurance models built on last century statistics break because their hazard maps assumed continuity. One more wrinkle: partial collapses. The AMOC isn't a single pipe. It's a network of formation sites and pathways. You can lose deep convection in the Labrador Sea, while the Nordic seas carry more weight, or vice versa, for a while. That creates regional expressions of the flip. The cold blob can intensify even as some parts of the overturning limp along, masking the severity if you only watch one index. But the integrated heat and salt budget still moves toward the weaker mode if freshwater keeps rising. Why does this matter now? Because early warning.
Signals suggest the restoring force is already dimming. Rising autocorrelation and variance in AMOC-sensitive fingerprints tell us the ball sits closer to the rim, close enough that a few unlucky winters could do the tipping. A newer, physics-based indicator, the minimum in AMOC-induced freshwater export at the southern Atlantic, adds a concrete gauge. In models that tip, that export weakens towards zero, then reverses as the circulation collapses. Reanalysis hints we're trending that way. Add observed subpolar freshening, thicker stratification, and an entrenched cold blob, and the ingredients for nonlinearity stack up. This isn't a centuries-away curiosity, it's within our lifetime's planning horizon. So the story arc shifts. We're not just tracking a slow decline we can hedge around. We're walking along a ridge, already leaning. The view may not change much for a while. Then you take one more step, and the ground drops away. The path back isn't the same trail. It's longer, steeper, and only available if the overall heat load falls well below the point where we slipped. Every ton of greenhouse gases, every gigaton of melt, leans that ridge a little further. Every cut buys time to stay on top. That's the choice set, and the clock runs on seasons, not centuries. 50-50, Europe's winter shock, and the jet stream twist. When the ocean stops handing Europe its quiet ration of heat, the atmosphere has to do the work. And it doesn't do it gently. Over the subpolar Atlantic, a weakened AMOC cools the surface relative to the subtropics. That sharpens the horizontal temperature gradient the jet stream feeds on. In winter, the jet can strengthen and shift, steering deeper, faster-moving storm systems across the North Atlantic. At the same time, blocking highs can lock in longer cold spells over Western Europe, because the background ocean warmth isn't there to blunt them. That's how a warming planet still deals out week-long freezes to a city like Dublin, radiators on full blast while global ocean heat hits records. Stakes first, what you actually feel. The cold arrives and stays. Your breath fogs in the hallway because the staircase bleeds heat. Condensation beads on inside window panes and turns to rime overnight. School texts say closed. Your power app pings with surge pricing at 7 a.m. and 7 p.m. You shuffle sockets to keep the kettle and space heater from tripping a breaker. The boiler groans. Gas storage that used to cover February now runs thin in January. Grids built for occasional snaps face sustained stress. Operators issue conserve now notices, voltage dips. Some neighborhoods roll through 1-hour outages at breakfast and dinner to keep the system up. Wind farms ride turbulent jets and then, under a blocking high, go still for 4 days. Interconnectors hum until ice accretes on lines, and crews crawl out at 3 a.m. with de-icers and headlamps. Transport doesn't keep up. Ice on runways and places that rarely needed de-icing crews becomes routine, with queues of flights waiting on glycol they didn't order enough of. Trains slow as rails shrink and points freeze. Leaf fall timetables look generous compared to blocked week timetables. Roads heave and crack under repeated freeze, thaw. Gritters run out of salt by Thursday. Bus doors freeze in their tracks. For families, it's the budget pivot. Heating over food or food over rent when the cold stretches a week beyond what they counted on. You move everyone into one room at night to keep pipes from freezing. You learn which cupboards hide external walls because the milk goes cold in them. Here's what actually plays out in the air, minus the jargon.
Think of the jet stream as a fast river of air that likes temperature contrasts. The cold blob south of Greenland cools the air above it, steepening that contrast with the warmer subtropics. The river speeds up and snakes more. Sometimes it kinks so deeply that a high-pressure dome parks over Europe, a block. Under a block, the storm track detours north or south, and the same cold, dry continental air just sits. No new air mass comes to flush it out, so overnight lows ratchet down day after day. When storms do break through on the block's edge, they hit sharper pressure gradients and carry more punch, stronger winds between the lows and highs. There's a paradox to precipitation you'll notice on your street. A strengthened jet can fling more frequent, intense winter storms toward the British Isles and the North Sea corridor. Yet less ocean heat under the storm track can reduce the moisture feed near Europe's coast, bringing more of the water out upstream. So some regions see fewer, drier weeks overall. Then the pattern flips for 48 hours and funnels moist air from the south, and you get a burst of heavy snow or freezing rain that snaps branches and downing lines. That's whiplash. 2 quiet, biting weeks punctuated by a storm that glazes every pavement and shuts the ring road. Meanwhile, the ocean surface answers back with reduced
Heat import. Parts of the subpolar North Atlantic can favor winter sea ice regrowth on the margins after a collapse, especially in sectors near the Labrador and Nordic seas. That doesn't mean Arctic pack ice roars back basin-wide, but regionally, new ice edges shift storm formation and wave fields. Coastal waters around Iceland and Greenland see rougher seas under a colder cap. North Sea waters may develop stronger stratification episodes under calmer spells, then overturn abruptly in storms, venting heat in bursts instead of a steady bleed, fuel for sudden squalls that catch ferries between harbors. Impact isn't just meteorological. A colder, stormier North Atlantic disrupts shipping lanes with more frequent, severe extratropical cyclones. Ferries cancel, ports stack containers, offshore maintenance windows shrink for energy infrastructure. Metro systems struggle with ice blown into open cuts. Points heaters fail in strings. Insurance models that price winters as windy and wet but moderate begin to price them as windy and freezing with clustered loss events. For cities, freezing fog and black ice become regular line items. Ambulance calls spike for falls and hypothermia. For rural regions, frozen topsoil delays spring planting. Then thaw and rain combine to waterlog fields, compressing the farm calendar into a narrow, riskier window. A micro-story brings this home. In County Meath, Maeve's neighbor Liam runs a small dairy. He used to schedule calving to beat the worst of February and hit the early March grass surge. Now the first March week sits under a blocking high. Nighttime lows drop below -10 for 5 straight days. The pasture crusts like glass. Pipes freeze in the milking shed despite heat tape. The smart meter shows red for hours each morning. The co-op texts about conserving power. He burns through his hay reserve a month early and phones a cousin 2 counties away for feed at prices he swore he'd never pay. On day 6, the wind flips. A coastal low barrels in, sleet ricocheting off galvanized roofs, roads close. The line to the creamery goes down. He watches the forecast on a cracked phone screen and starts calculating losses. One more knock-on, energy systems. Europe's transition bet heavily on wind and interconnectors that smooth out variability across regions. In a colder, more blocked winter regime, wind output can be feast or famine. Long, still frigid spells under high pressure. Then roaring days when turbines must feather in gales. Power markets spike just as heating demand peaks. Gas peakers run hard if they exist. If not, rolling shortages hit at breakfast time. Crews de-ice transmission lines by helicopter. Substations trip on ice and salt fog. Planners tasked with resilience suddenly need cold, hardy transformers. More storage measured in days, and pricing that doesn't crush households when the jet stream decides to camp. Through all of this, remember the scale. We're not talking about every winter turning into 1963. We're talking about shifting odds and more clustering of extremes. The background state tilts toward colder European winters compared to a world with a strong AMOC, even as global mean temperature climbs. That's the paradox you'll hear at the pub. Record global heat, record local cold snaps. It shows up in the data and in high-resolution simulations that collapse the overturning. Stronger westerlies over the North Atlantic, deeper storms, and less winter precipitation in parts of Europe despite louder weather. The fingerprints are consistent with what Maeve heard on the radio. Unusual, then record-breaking, then simply the forecast. Sikitsi. Rain belts on the move. Monsoons, drought, and flood. While Liam counts bales in County Meath, the tropics adjust their aim. Shift the Atlantic's heat, and you tug the planet's main rain belt, the ITC, off its usual track. With a weakened AMOC, the North Atlantic cools relative to the south. The ITC follows the warmth, edging southward. Think of it like a fire hose drifting a few streets over. Every house that counted on that water suddenly runs dry, while the next neighborhood floods. It sounds abstract until you stand in a village that counts weeks to the first planting rain, and those weeks stretch stakes first. When the rain belt moves, food security moves with it. Planting windows shrink or arrive late. Seeds rot in dust or drown in a weekend. Reservoirs miss refill seasons, and ration cards return. Cities built around predictable downpours see gutters run dry for a month and then suddenly overflow in an afternoon. For people, it's harvest yields, water taps, and flood lines etched higher on living room walls. It's food prices on a chalkboard doubling by Thursday. Here's what unfolds. Over the tropical Atlantic, a south-shifted ITC boosts convection closer to the equator and into the southern hemisphere. West Africa feels that as a rearranged monsoon. The Sahel's northern edge retreats, the core rains concentrate farther to south, and the season's rhythm turns erratic. Some years bring a shorter, sharper burst. Others deliver a late, weak onset that leaves seedlings stranded in hot dust. Farmers who used to plant on the third storm now wait for a fourth that comes 2 weeks late, if at all. Wells drop by a hand's length. Pasture browns early. Herders sell animals cheap, and meat prices still climb because grain to feed the rest is scarce. Meanwhile, across the ocean, the Amazon's water budget changes. With the ITC displaced and the Atlantic temperature gradient altered, moisture transport from the ocean into the basin weakens in parts of the year. The dry season stretches into western and northern Amazon. Streams shrink to strings of warm pools. Fish die-offs dot banks that smelled of rain for generations. Trees close stomata to save water, dropping leaves early. Lightning finds drier crowns and fires run longer. In the south, some models find wetter seasons after an overturning collapse, but timing matters as much as totals. A late season dump can still be a net ecological stress if early dry months scorch. Saplings fail and canopy gaps widen. The forest's resilience, rooted in deep groundwater and cloud feedbacks, faces a new pattern it didn't evolve for, with knock-ons for regional rainfall recycling that cities depend on. South Asia isn't spared. The South Asian monsoon feeds on land, ocean contrasts, and upstream moisture pathways that feel the Atlantic's push. A weaker AMOC tends to reduce the northern tropics' heat draw, weakening the large-scale thermal contrast that powers the monsoon circulation. On the ground, that can mean a delayed onset, a sputtering first phase, and long breaks between active spells. Rice paddies crack in June, then floods slam them in August when stalled lows dump a month's rain in 3 days. The crop calendar becomes a gamble. Transplant earlier and risk drought, wait longer and risk flood. Groundwater pumps hum for hours and pull up sand. Diesel bills eat margins. Urban India and Pakistan watch reservoirs skate toward dead storage, and then jump back with a single storm that also floods, underpasses, clinics, and shops. Unknown to them, across the Pacific, the Caribbean, and Central America ride the same seesaw. With an altered Atlantic gradient, tropical cyclone genesis zones and easterly waves change their behavior. Fewer but slower storms can sit over mountain valleys, wringing out catastrophic totals. The rainy season feels like a string of near misses, then a bullseye. Landslides take the same hillside twice in 5 years. Coffee growers lose blossoms to drought, then cherries to rot. Concrete examples are everywhere when the hose drifts. West Africa, millet sown on the second good rain fails twice. Goats are sold at half price. School lunch programs switch to 1 meal a day. Market rice jumps 20% in a week after an export ban abroad. South Asia, a 2-week break in July kills transplanted paddy. Then a cloudburst drowns storage pits. Onions and cooking oil spike. Ration queues lengthen. Migrant labor flows to cities that are already rationing water. The Amazon, Smoke from a longer dry season closes airports. Barge traffic slows on shrunken rivers, so soy and fuel arrive late and cost more. Towns run generators all night. Clinics treat respiratory cases in corridors. Back to West Africa for a micro story. In northern Ghana, Amina's cooperative keeps seed in a locked trunk. Their rule was simple: plant after the first 2 solid rains. This year, the first arrives in late May. The second doesn't come. Daytime highs beat the seedlings down. They replant in mid-June after a dusty squall. Then the sky opens. 4 days of sheets. The new channels they dug last year aren't enough. Water jumps the bank, eats a path through the maize rows, and fills the well with brown. The co-op's grain bank opens early and empties early. The price board in town changes twice a day. They salvage what they can and spend the evening tallying debt. In the U.S. East Coast corridor, the knock-on isn't a monsoon, but storm track and moisture feed. A different jet configuration funnels slow-moving nor'easters that stall over coastal plains. Warmer air holds more moisture, and with altered steering currents, those systems dump longer. River basins already swollen by sea level rise see compound events. Surge at the mouth, rain inland, and tides that won't let the water out. The map of once-in-a-hundred-year floods redraws itself every few winters. Meanwhile, northeast Brazil and parts of West Africa live with whiplash, drought that primes soils to shed water, followed by convective bursts that do exactly that. Urban drainage, designed for old intensities, caves under new peaks. Rural roads vanish into gullies. Insurance doesn't cover smallholders. Relief arrives late. People move to towns on rumors of steadier work, and towns strain underwater rationing that used to be a summertime story and is now a March to October reality. Food staples sit in the crosshairs. Wheat belts in Europe face colder, wetter springs. Rice in South Asia sees erratic transplanting windows. Maize in the Sahel shifts south with the rains, crossing borders and customs that don't move as easily. Global markets feel it. Exporters pause shipments after a bad monsoon. Importers scramble, and price spikes ripple through places that never heard the acronym AMOC. A bag of rice in Accra, a loaf in London, both carry the cost of a rain belt nudged a few hundred kilometers. Food inflation becomes a background noise in headlines. For households, it's fewer proteins and thinner porridge. So while Maeve scrapes ice from a doorstep in Ireland, Amina watches clouds misfire over a field in Tamale. Different latitudes, same cause. A circulation you can't see from shore shifted the line where air rises, and everywhere that depended on that line learned how fragile normal can be. The ITC isn't a trivia term. It's the switch that decides whether seed sprouts or spoils, whether a reservoir fills or a tap hisses, whether the market board chalks the old price or wipes it clean by noon. The food system dominoes. Follow the cold and the rain belts into the ocean and the fields, and you start to see the chain reaction. Fisheries first. The North Atlantic's productivity depends on how nutrients move from deep to surface. When the overturning weakens, that vertical conveyor gets patchy. Stratification holds nutrients down longer. Mixing happens in bursts, not steady pulses. Plankton communities shift. Less of the cold-loving species that time blooms with spring light. More opportunists that peak at odd times. Juvenile cod and herring miss the buffet they evolved to meet. Recruitment drops even when adult fish still look plentiful. That's the quiet beginning of fishery collapse. The nursery empties first, then the docks. Here's where it gets concrete. A trawler out of Reykjavik hauls in nets leaner than the skipper remembers from his father's stories. Sensors show a warmer layer at 100 meters and a fresher cap on top. Nutrients trapped below a lid. Capelin leapfrog north and east. Mackerel lunge into new grounds, sparking quota fights from Scotland to Norway. Iceland and the EU argue over slices of a pie that's sliding off the table. On the dock, the price board jerks. Cod up 12% this week. Capelin off the board. Mackerel quota pending. Onshore. Processing plants can't plan shifts. A freezer warehouse sits half empty in January, then overflows in March when a pulse finally arrives. Forklifts idle 1 month, run 24/7 the next, and pallets thaw on the bottleneck. Meanwhile, the subtleties matter. If spring stratification locks in too early, under calmer, colder skies, the classic spring bloom comes late or in 2-week waves. Zooplankton, tiny grazers that feed larval fish, Mismatch with larvae hatching on an old schedule. That's a silent failure you don't see until 2 years later, when a cohort never shows in surveys. Add acidification and oxygen drops in subsurface layers, and the margin for error shrinks. Arctic fisheries look like the next frontier on paper. In practice, ice, storms, and fragile ecosystems make them a risky bet. Managers call it adaptive quotas. Crews call it boats tied up while bills come due. Now walk inland. Europe's growing seasons tighten under colder, wetter springs. Wheat wants a clear window to tiller and set heads. Instead, tractors bog in April and cold snaps scorch young leaves. Harvests slide later into wetter autumns and combines chew mud. Quality downgrades, from bred wheat to feed, cascade into prices. Rapeseed flowers during a chilly spell, bees stay grounded, pod set suffers. In southern Europe, the flip side bites hotter, drier spells between erratic storms as storm tracks shift, stressing vines and olives. In the UK, a farmer like Liam swaps seed varieties for cold tolerance and disease resistance, but inputs climb and yields wobble. At the mill, buyers mark down protein content. Loaves shrink by a slice and the price tag doesn't. Outside Europe, the monsoon wobble shows up in export bins. A South Asian rice harvest with a delayed onset pushes global rice prices up 15% in a month. If two exporters announce temporary bans, wholesale prices in West Africa jump 25% by Friday, and retail bags grow a third lighter for the same sticker. A second weak Sahel season trims West African millet and pushes feed prices higher for poultry. Brazil's soy belt catches out-of-season downpours and a longer dry spell, swinging output regionally by millions of tons. The story isn't one failure, it's synchronized volatility. When 2 or 3 breadbaskets stumble in the same year, importers draw down reserves, exporters float trial export bans, and futures markets whiplash. Limit up on Monday, limit down by Thursday. Every link brings a secondary hit. Fertilizer production leans on steady gas and power. A colder European winter with a blocked jet spikes energy prices. Ammonia plants throttle back. Nitrogen prices jump 30 to 60% into spring planting. Farmers cut application rates and accept yield risk, or they borrow at ugly terms. Insurance used to buffer some of this, but actuarial tables trained on the past mispriced clustered losses. Premiums climb, deductibles widen, and some regions drift into uninsurable for multi-peril crop coverage. Lenders notice. Balance sheets age in dog years. Equipment upgrades slip. A broken dryer becomes a harvest-long headache. Shipping feels the weather too. More frequent, intense North Atlantic storms stretch transit times by days, flip reefer containers, and close ports on short notice. Grain held in damp air cakes and fails quality tests. Fumigation becomes routine. Refrigerated fish loses shelf life waiting for windows. Best Buy, dates get shaved a week the moment a ship misses berth. Just-in-time inventory turns into just-in-case stockpiles, tying up capital in warehouses. Supermarkets hedge with more contracts and fewer suppliers, which sounds stable until 2 suppliers sit on the same river that floods or the same port that stalls under a
block. Now zoom into the places where delays become dinner. Ports, pilots wave off in 45-knot gusts. A stack of reefers trips a breaker. The backup generator sputters in salt fog. Customs clears perishable containers last because the IT system crashes, and 1,000 kilos of lettuce turns to slurry. Warehouses, the chiller fails during a surge. Alarm techs arrive at 3 a.m. Staff forklift pallets into rented trailers running off diesel. A week later, the bill for fuel wipes the month's margin. Supermarkets, empty spaces on the fish shelf get temporarily out of stock stickers. Tuna swaps for sardines. Salmon fillets shrink and grow pale. Bakers switch flour blends, bread rises shorter, a quiet sign reads, "Due to supply issues, limits apply, 2 units per customer." Micro story. In Rotterdam, Fatima manages procurement for a grocery chain. Her dashboard lights up. Norwegian salmon short, UK wheat downgraded, Spanish citrus delayed. She shifts to Icelandic cod, then learns the quota's in dispute. She swaps to Canadian wheat, a nor'easter parks over Halifax, and the ship misses its slot. Her CEO wants prices steady to keep market share. Her spreadsheet says raise canned fish by 9% and bread by 5% or take the loss. She delays a week,
burns margin, and hopes the jet stream unblocks. In week 2, a cold snap spikes power prices. Her cold store contract hits a surcharge. She greenlights a 12% hike on frozen fish and pulls the ad for family salmon packs. Customer complaints climb, shrink theft rises, store managers ask for security on delivery days. Finance turns weather into numbers. Sovereign debt for countries that import food and fuel at the same time widens in spread after a rough monsoon and a cold European winter sap foreign reserves. Credit rating agencies start issuing notes on circulation risk exposure. Ports seek capital for higher keys and wind hardening. Insurers demand adaptation plans before renewing. Derivative markets invent AMOC risk indices tied to subpolar salinity and jet latitude, because someone always tries to price the unpriceable. Food manufacturers add weather escalators to contracts. If grain prices move 20% in a quarter, invoices step up automatically. Adaptation choices stack up. Fisheries councils push dynamic quotas and bycatch rules tuned to real-time data, if politics allows. Farmers trial cold hardy wheats and drainage upgrades, plus more on-farm storage to wait out wet harvests. Cities expand cold weather shelters as a permanent line item. Governments consider strategic grain reserves again, this time with rotation schemes that don't collapse under politics. Grid operators add storage and interseasonal planning for longer freezes. Processors add redundancy, 2 mills instead of 1 giant, 2 cold stores on different grids. None of this is abstract. It lands in lunchboxes and invoices and phone calls at dawn. A circulation you can't see from shore puts a thumb on the scale, and the food system feels the weight in every link. Prices on the chalkboard change mid-week. Limit 2 per customer signs become normal. A port delay on Tuesday is a bare shelf on Saturday. That's what a weaker ocean conveyor looks like in a supermarket aisle. Creepiest storms, sea level, and coastal risk. While cargo planners hedge fish and grain, the ocean lines up a different bill. A weaker AMOC reshapes the playground for storms. Over the North Atlantic, sharper temperature contrasts and altered currents steer extratropical cyclones onto new tracks and change how long they linger. Nor'easters feed on that gradient. With less ocean heat released north of the Gulf Stream, some storms deepen farther offshore, then hook and stall as blocking patterns set. That buys them time to stack tides, push surge into bays, and dump bands of heavy snow or cold rain over the same counties for a day too long. Stakes first. Coastal cities don't budget for stalled. Transit tunnels take on brackish water that fries relays. Hospital generators hum in basements at the exact height maps said wouldn't flood until mid-century. For homeowners, it's the math of repeated repairs on houses whose mortgages still have 20 years to run. For small businesses on working waterfronts, every flooded freezer is a layoff lurking 1 storm away. Here's what actually happens. When the overturning slows, the dynamic sea level along the U.S. East Coast rises relative to the open Atlantic. The pressure gradient that a strong AMOC maintains flattens, allowing water to pile a bit more against the shelf. Add thermal expansion and land subsidence in places like the mid-Atlantic, and high tides ride in higher. A nor'easter that once pushed 2 feet of surge on a spring tide now pushes 3. Streets that used to flood on a handful of king tides each year now see salt water twice a month, then weekly, then most days with an onshore breeze. Now zoom into a compound flood, the kind you feel, smell, and mop. It starts with a spring tide, that already. Crowd storm drains. The barometer falls. Rain hits for 12 hours straight, the kind that drums on the letterbox and turns the air metallic. Gutters fill with leaves, then with brown water that smells faintly of diesel. The wind swings onshore. Surge lifts the harbor a foot, then 2. The outfalls that should spit water into the bay go silent because the bay is higher than the pipes. Stormwater has nowhere to go but back through grates and up through toilets. You step into your cellar and feel cold brine around your ankles. The power stays on until a salt mist bridges a switch at the substation. Lights blink. The sump pump coughs once and dies. By morning, the water line on the drywall is waist high in blooming white crystals. Meanwhile, storm tracks adjust. Stronger, more poleward jets can send the fiercest extratropical cyclones over higher latitudes. But the ones that do aim for the northeast often move slower under blocking. Slow is the problem. Rainfall totals climb not just because warmer air holds more water, but because the system doesn't leave. River basins from the Carolinas to New England take hours longer to drain.
partly because sea level at the coast sets a higher base. The tide at the mouth becomes a cork. Sewage plants switch to bypass to keep from blowing lids. Boil water notices show up on phones at 3 a.m. Subway crews stack sandbags at vent gratings. Buses detour around corners that look like ponds. Hurricanes complicate the picture. Their overall numbers may not jump, but the ones that form can draw more moisture and stall more often as background steering currents weaken in places. Over warmer coastal shelves and against higher baselines, they don't need Category 4 winds to be catastrophic. A slow Category 1 that parks near the fall line forces water into estuaries on one side while rain piles on the other. Think less wind machine and more fire hose. Houses far from the beach find themselves in the new floodplain. Elevation certificates go out of date between refinances. Appraisals come back with red flags. Compound events become the new baseline problem. A stalled nor'easter arrives 2 days after a spring tide and 24 hours after 6 inches of rain upstream. Surge piles into a harbor. Swollen rivers meet a closed door. Runoff jumps curbs and looks for basements. Insurers call it correlated risk. Homeowners call the plumber at midnight. After the water drops, salt eats wiring, mold blooms behind drywall, and the next premium arrives with a letter about updated risk zoning. Now add the infrastructure failures that turn a bad storm into a week-long crisis. Power. Coastal substations arc in salt fog. Corrosion trips relays. Crews wade in waders to hose down gear. Rolling blackouts follow because redundancy assumed dry feet. Tunnel portals take on brackish water, track circuits short, brake resistors pop, pumps run until they seize, service maps go gray for days. Water and wastewater, low-lying plants flood, clarifiers overflow, combined sewer overflows pump straight to rivers, boil and don't flush, collide on the same notice. Communications, telecom huts and floodplains go under. Cell towers run on generators that run out of diesel when roads stay closed. Point-of-sale systems go down just when stores reopen. Ports and supply chains feel this in schedules. Pilots wave off more often as crosswinds top thresholds. Container yards elevate stacks, then learn cranes were never spec'd for gusts that now show up twice a winter. Repair windows for offshore wind farms and telecom cables shrink as subpolar storms grow teeth. Fishing fleets look at wave forecasts and stay tied up for strings of days that used to be singles. When they do sail, they aim for tighter weather windows and carry more fuel, eating margins. For households and city budgets, the money story gets rough. Premiums step up yearly, deductibles jump from $1,000 to $10,000. Exclusions multiply, first surge, then groundwater, then nuisance flood. Some carriers quietly non-renew entire zip codes, others cap policies. State-backed insurers of last resort balloon and raise levies on everyone. Mortgages in new special flood hazard areas stall, closings fall through, sellers cut prices, buyers demand concessions for elevating mechanicals. City bond ratings come with climate riders. Capital plans reshuffle from parks to pumps. Micro story. In Boston, the Ridleys live 3 blocks from the harbor. Sunny day floods used to be a meme, some guy kayaking the corner. Now the school bus reroutes twice a month. In February, a nor'easter runs up the coast, slow enough to visit for breakfast, lunch, and dinner. The storm surge hits near the day's second high tide. Water laps over the seawall and down into the tea station. The Ridleys pull rugs and lift couch legs onto paint cans. The sump pump hums, then sputters. They text their downstairs neighbor, who already left for her overnight shift at the hospital. By morning, the power's out. By evening, the adjuster says their policy doesn't cover the boiler because that's flood, not wind. A week later, their insurer sends a polite notice. Non-renewal at term due to aggregate exposure. The bank emails about force-placed insurance that costs triple. There's one more quiet shove. Coastal erosion. With mean water levels higher and storm waves more frequent, dunes and marshes erode faster. The marsh that used to knock a foot off surge heights now sits drowned too often to keep up, losing the sedge that traps silt. Breakwaters and seawalls buy time, but they reflect energy that comes ashore somewhere else. Managed retreat moves from planning documents to whispered kitchen table conversations. Realtors stop showing certain blocks on the rainiest days. Inspectors sniff for mold before they check the roof. The timeline tightens.
What used to read as mid-century risk shows up in utility outage logs and insurance filings this winter, not in 2040. Tidal flooding that was annual becomes monthly, then weekly in a few years for low-lying neighborhoods. The first mortgage lenders add climate conditions to loans in flood-prone tracts. City councils shift line items to permanent pump operations, higher seawalls, and elevating switchgear now, not in the next capital cycle. Homeowners face 3 choices on a 5-year clock: pay to lift, pay to leave, or pay higher premiums until the carrier leaves first. All of this tilts risk from occasional to chronic. The baseline creeps up, the storms take longer, the drains clog on the ocean side. It's not one monster event. It's a string of impacts that add up to a new map of where it's practical to live and work. And because the AMOC is a basin-scale lever, the same physics pushing water into South Street Seaport nudge it into Norfolk, into Charleston, into Miami's roads that gleam with salt crystals every afternoon. The question isn't whether the coast notices. It's how many quiet days are left between notices. 9. The timeline. Sooner than we thought. 3 decades ago, podium talk was soothing. The AMOC might weaken this century, but a full collapse was very unlikely. Translation people heard, check back in a few centuries. That comfort rested on 2 crutches. First, earlier models blurred the very choke points that matter: narrow overflows, fjords, and storm force mixing. So thresholds looked farther away and flips looked slow. Second, industrial aerosols cooled the North Atlantic surface through the mid to late 20th century, masking greenhouse warming. As aerosol emissions declined after the 1980s, 1990s, and observations sharpened, the mask slipped. The signals, freshening, thicker stratification, the cold blob, Gulf Stream gradient changes, stepped out of the fog. And a new line of evidence arrived in force: early warning physics, critical slowing down, and a physics-based budget metric, freshwater transport diagnostics. What changed in the science? Concretely, observations expanded. Since the early 2000s, the rapid array at 26.5 degrees north, satellite altimetry, tide gauges, Argo profiles, and Grace FO gravity data on Greenland's mass loss built a coherent picture of a sluggish system. Not from one magic instrument, but from many that agree on direction. Resolution improved. Newer ocean models and eddy-resolving hosing experiments captured narrow sills and overflow pathways, e.g. Denmark Strait, Faroe Bank Channel, and the eddies that shuttle heat and salt. Result: thresholds appear at lower freshwater forcing, and once crossed, the decline unfolds on months to years timescales. The mask faded, declining North American and European aerosol emissions since the 1980s, removed part of the surface cooling screen over the North Atlantic, revealing the greenhouse signal and making the cold blob fingerprint more diagnostic of reduced heat import rather than just aerosol wind noise. Early warning indicators matured. Studies applying critical slowing down, rising autocorrelation invariance to AMOC-sensitive fingerprints, plus a physics-based indicator, the AMOC-induced freshwater transport at the southern Atlantic boundary, now show trends consistent with the system losing resilience and approaching a minimum in that transport on the way to a flip. This is the pivot from centuries to decades. Risk is no longer parked in the year 2300. Multiple analyses place a non-trivial window in the mid-century decades, the 2030s to 2060s, with some estimates narrowing toward the 2040s, 2050s, under continued forcing. Others keep the threshold further out and stress uncertainty. The IPCC still calls a 21st century collapse unlikely, but with low confidence on exact thresholds. That's the scientific tension. Conservative baselines meeting sharper tools make the urgency tangible. The approach can look boring for years, then flip fast. Approach: rising subpolar freshening, thicker winter caps in the Labrador-Erminger Nordic seas, a persistent cold blob, clustered coastal sea level bumps along the U.S. East Coast, and early warning stats ticking up. Headlines feel routine. Transition: in high resolution, runs that capture key sills and eddies. The main AMOC index drops most of the way to the weak state in months to a few years. Surface impacts: colder, blocked European winters, a south-shifted ITZ ed. Altered storm tracks emerge within a few seasons to several years. That's a budget cycle, not a dynasty. What's robust versus contested? Robust. The AMOC today is weaker than in the 20th century. Subpolar freshening and stratification are rising in key formation regions. The cold blob persists in independent SST datasets. Greenland mass loss is accelerating, and early warning indicators behave as theory predicts near a tipping point. Contested. The exact freshwater threshold, how winds and gyres pace the approach, and whether internal variability can mimic early warning trends over recent decades. Climate noise is loud and clean, observing windows are short. That's why we triangulate across methods. What to watch now? Dashboards tied to physics, not vibes. Salinity and stratification where it hurts. Upper ocean salinity and winter mixed layered depths in the Labrador, Erminger, and Nordic seas. Moored arrays, Argo winter profiling floats. Thicker fresh caps and shallower winter mixing mean less deep formation. Deep water formation proxies. Post-storm changes in heat and oxygen inventories that reveal how often convection punches deep. Fewer deep resets equals fading resilience. Gulf Stream gradients and coastal sea level. The sea surface height/density gradient across the current from altimetry and hydrography, plus de-tided, de-subsided anomalies along the U.S. East Coast. A slacker gradient with clustered coastal bumps points to a gentler overturning. Freshwater transport budget at the southern boundary. Routine estimates from reanalyses and ship sections drifters. In models that tip, this transport approaches a minimum before flipping sign. Trends toward that minimum are a red flag. Early warning statistics consistently applied. Rising autocorrelation variance in independent AMOC fingerprints, SST dipoles, density contrasts, with transparent methods and open data for community cross-checks. Why this matters to planners right now? The timeline you can influence is the runway before the rim. Emissions control the slope of Greenland's melt and the pace of Arctic freshening. A slower push can shift a plausible window from the 2030s, 2050s into the 2050s, 2060s. Buying time to harden grids, ports, and food systems, and to expand observing lines. A faster push compresses the window into 1 or 2 election cycles. The difference between a 2035 to 2055 risk window and a 2055 to 2075 window is the difference between planning for 1 climate or 2 within the same asset lifetime. Reality check for headlines, collapse next year, and nothing for centuries are both strawmen. The AMOC is already weaker. Multiple independent lines point the same way, and the plausible risk has entered the planning horizon. You may not see the flip on your street this winter, but living through the transition is no longer a remote scenario. And once the threshold goes, the changes arrive on the timescale of budgets and elections, not ice sheets and empires. That's why we can't bet on slow. If we can't guarantee a gentle slope, we need cushions now. Cut the push, emissions. Watch the rim, observations, and early warning dashboards, and harden the systems that fail first when the jet parks or the rain belt moves. The next step is turning that urgency into concrete buffers you can fund this fiscal year. Buffers and brake pedals. What can still help? We can't change ocean geometry, but we can change the push. Emissions are the first brake. Every ton not burned slows Greenland's melt curve and eases Arctic freshening. That buys seasons, maybe years, on the approach to a threshold. It doesn't guarantee safety, but time is the currency every adaptation plan spends. CO2 cuts are the big lever. They trim the long tail. Paired with that, methane and black carbon are the quick-turn knobs. Methane controls near-term warming, leak detection, pipeline fixes, and landfill capture cool the next decade's baseline. Black carbon from diesel and cook stoves darkens snow and ice, speeding melt. Clean burners, filters, and fuels keep sunlight from being weaponized against the cryosphere, consistent with cryosphere and air quality literature. There's a temptation to reach for a silver bullet over the subpolar Atlantic. A dam here, a salt dump there. Reality is less tidy. Local geoengineering faces scale and ethics. You can't meaningfully resalt a basin the size of half a continent, and you don't want to experiment with ocean mixing when fisheries and weather ride those layers. What's left are careful, reversible interventions. Restore sea ice resilience by cutting soot and limit warm Atlantic water intrusions into Greenland's fjords by protecting the coast's cold shelf currents from anchoring industrial warming hotspots. Even then, the main brake is still turning down the global furnace. If we can't bet on slow, we need cushions. Energy first. Europe's grids shaped for mild winters need cold resilience. More storage to ride week-long freezes, interconnectors harden for ice and wind, and demand response that pays households to shift load without punishing the poor. Heat pumps cut gas dependence, but they need backup heat for block still nights. District heating with thermal stores can carry a city through a stubborn high. Weatherizing homes, insulation, sealing, better glazing, doesn't just lower bills, it shaves peak demand that crashes grids. In colder snaps, it keeps bedrooms habitable when power flickers. Food systems need slack. Strategic grain reserves sound old-fashioned until export bans stack. Modern versions rotate stock, publish rules, and coordinate regionally so one country's hedge isn't another's panic. Farmers need drainage and water management for colder, wetter springs, subsurface tiles, raised beds, and controlled traffic lanes that keep heavy equipment from cementing soil. Seed banks can accelerate the release of cold-tolerant cereals and oilseeds alongside varieties tuned for shifted rain timing. On-farm storage buys negotiating power when harvests collide with storms. Insurance has to evolve. Parametric policies that pay on rainfall or temperature thresholds can deliver cash fast, even if traditional loss assessment bogs in mud. Ports and coasts need room to breathe. Elevating substations and moving switchgear upstairs sounds dull until salt water eats a city's nervous system. Floodgates that keep surge out also need pumps that move rain when the tide refuses. Marsh restoration and living shorelines aren't quaint. They're friction that bleeds energy from waves and buys time before walls must rise. Where walls are inevitable, design them to fail safely and with a plan for what happens behind them. Sacrificial ground floors, pop-up barriers, roads that double as canals on the worst day. Data is the other brake pedal, because seeing the bend early is half the game. Expand the mooring lines beyond 26.5 degrees north to catch the overturning's limbs. Tie them to gliders and Argo floats that profile salinity and temperature through winter. Put smart buoys in the Labrador and Erminger seas that watch mixed layer depths as storms roll through. Satellites will keep weighing Greenland, Gracefo, and its successors, but we need sharper coastal sea level gauges that separate subsidence from dynamics. The physics-based early warning, the freshwater transport minimum at the southern boundary, needs routine estimates from drifters and ship sections, not just reanalysis. And all of it should flow into open dashboards where a farmer, a mayor, and a grid operator can see the same needle moved. Adaptation lives and dies on micro decisions. A council that switches procurement to cold-rated transformers before the next winter. A fishery that sets dynamic closures based on real-time temperature fronts, so spawning isn't blindsided by a shifted bloom. A hospital that moves its generator. A lender that offers low-interest retrofits for insulation in postcodes flagged by new jet patterns. None of these headlines will say, AMOC, but they're the difference between a shock and a bruise. One last buffer isn't physical, it's social. Transparent risk communication avoids two traps: doom that paralyzes and denial that delays. People can handle risk window and watch these tripwires if the next steps are clear. The ocean won't negotiate, but it will respond to the heat we add and the time we take to prepare. We still control both. Sources for the risk framing include peer-reviewed early warning analyses, critical slowing down, and process indicators, freshwater transport, alongside observational arrays. For example, rapid at 26.5 degrees north. Human stories, life on the edge of a flip. Start in Ilulissat on Greenland's west coast, where the fjord spits ice with a sound like distant artillery. Anna steers a small boat through brash ice her grandfather said was rare this late in summer. The glacier face used to sit farther down the fjord, taller, steadier. Now the front calves twice before noon. The harbor water tastes faintly sweet at the surface, a thin lens of melt that clings to the top. Anna shifts her nets deeper because the cap deceives sonar. Capeland arrived early last year, then vanished. Halibut lingered, but their fat stores were odd. Warmer water at depth, her father muttered. On shore, the fish plant braced for a surge that never came, then shut for 2 weeks when storms pinned the fleet. Anna's brother talks about a job at the airport. She runs the numbers on fuel, rope, repairs, and a payment on a boat that owes its life to an ocean that no longer keeps its habits. Across the water, in Norfolk, England, Tom walks his wheat in boots that sink and suck. He planned his field drainage after the wet autumn of 5 years ago. It helped until cold-blocked high pressure sat for 8 days in March. The frost locked the topsoil, the next storm sheeted water across the surface. He delayed drilling, then drilled anyway because the contract dates didn't budge with the forecast. In May, a cold snap nipped the tips. In June, his agronomist pushed a fungicide he hadn't budgeted for. Tom calls his insurer, who sends a leaflet about changing weather patterns and a premium adjustment he can't meet. He trims nitrogen to save cash, watches the head set thin, and thinks about his father's advice. Don't chase every season. But the seasons keep chasing him faster. Meanwhile, in Senegal's peanut basin, Mariama rolls a seed between her fingers and waits for a second decent rain. The village used to move in rhythm. Plow, plant, weed, harvest. Now the first storm teases, then silence. She planted once, twice, and lost seedlings both times. When the rain finally comes, it comes hard. Water eats a channel through the field she terraced last year with neighbors. Her son wants to leave for Dakar. The cooperative discussed drought-tolerant varieties, but the delivery truck arrived late and half the sacks were moldy. Mariama sits beneath a tin roof in the heat, listening for thunder and counting the sacks of millet they set aside for lean months that now stretch. Up the U.S. coast in East Boston, Teresa times her life by tides. The calendar says school, shifts, sleep. The harbor says otherwise. A new bus route avoids the lowest blocks on king tides, but winter storms ignore reroutes. In February, a nor'easter creeps in slow. Teresa checks the sump pump, lifts the rug, texts her downstairs neighbor. The water doesn't roar, it rises. She keeps towels by the door and a list of phone numbers on the fridge. After the storm, a contractor quotes a number that might as well be a phone number. The landlord talks about raising the building or selling. Teresa thinks about her mother's apartment 2 subway stops away. Higher up, smaller, already full. Back in Greenland, Anna's uncle remembers winters that felt heavier. Now, storms come more often, more erratically. Sea ice forms later and breaks earlier, and the old routes between islands feel less certain. He says the ocean sounds different when the cap is thick, quieter, duller. This year it stayed noisy longer. The locals talk about fjord water that doesn't cool like it did. Scientists came through with instruments, asking for help placing sensors. Anna ferried them to the mouth, where the water feels layered, fresh on the tongue, warm on her knuckles at depth. In Norfolk, Tom's neighbor Sarah installs a secondhand grain dryer because harvest keeps slipping later into wet. The bank wants collateral. She signs over a tractor. She and Tom split a load of new seed, cold-tolerant, disease-resistant, expensive. At the village hall, the energy co-op pitches heat pumps and insulation grants that close before anyone finishes the paperwork. The parish clerk mentions a fund for flood barriers on the lane. Nobody says the acronym, but everyone's eyes flick to the sky when the forecast uses the words stalled and blocked. In Senegal, Mariama's sister sends voice notes from Accra about work in a market. The family debates which child leaves next. A visiting agronomist sketches rain bands moving on a map and talks about storage, insurance, and new planting rules. Plant by soil moisture, not date. He leaves pamphlets. Mariama keeps the seed trunk locked, like her mother told her. But the lock doesn't make clouds. In Boston, Teresa's daughter asks why.
There's street floods more than the one up the hill. Teresa says the ocean is pushing. When the power flickers on, she makes hot chocolate and checks the neighbor's boiler. The next letter from the city talks about grants for elevation, about a new seawall, about community meetings in a school gym that still smells faintly of salt. Different languages, different latitudes, the same edge. None of them voted on a conveyor they can't see. They feel it slackening in hay bales, in ice, in seed, in salt water under a front door. And they're already choosing stay or go, spend or save, risk or hedge, micro decisions stacked against a macro shift. Why we underestimated the threat. Step back and you see 2 kinds of fog, the oceans and our own. The science didn't start from zero. It started from tools that blurred the very places that mattered. Early global models ran oceans with coarse grids, cells so wide they smoothed narrow sills and fjords where deep water forms. The Labrador Sea's convective plumes looked like broad blobs. Eddies that shuttle salt and heat key to resilience were parameterized, not resolved. With the rough edges sanded off, thresholds sat farther away and collapses took their time. The system looked sturdy because the map hid the cracks. Then there was noise, real physical noise. The North Atlantic breathes on its own. Winds shift, gyres fatten and thin, winters swing between stormy and calm. Industrial aerosols added another layer, cooling the surface and masking greenhouse heat for decades over the Atlantic. In that fog, signals of weakening looked like weather. You could point to a harsh winter that punched open deep convection and say, see, it's fine. You could point to a warm, stratified year and say, just variability. We did both, because the records were short and the variability was loud. Institutional caution played a part. Big assessments like the IPCC don't leap on the latest curve. They average across models, assign confidence, and keep to the median. That's good practice when you're pricing most risks. It's less helpful when the tails eat the table. The AMOC sat in the low likelihood, high impact box. Flagged but buffered by phrases like, very unlikely this century. Communicators worried about crying wolf. Policymakers heard the adverb and filed it under later. Meanwhile, specialists published warnings that sounded like footnotes compared to the drumbeat of global average warming. Cognitive bias did the rest. We like lines, not cliffs. Our planning playbooks assume incrementalism. Today, plus 2%. A nonlinear circulation with hysteresis doesn't fit. When models in the 2000s said weakening, not collapse, it synced with that bias. When early studies of cold blob causation split between winds, aerosols, and AMOC, it was easy to pick the least alarming mix. We're pattern hunting creatures. When the pattern is a switch, we look away. At a mismatch of metrics, we tried to measure a basin scale machine with local yardsticks. The rapid array at 26.5 degrees north gave us a precious, direct index, starting in the early 2000s. Before that, we had fingerprints, temperature patches, sea level gradients, density contrasts. Each proxy carried caveats. Winds can paint sea surface temperatures, coastal sea level has subsidence, density at one depth isn't the whole overturning. In papers, the caveats read like caution. In headlines, they read like doubt. The prudent, here's what this can't show, overshadowed the consistent, here's what it does. There was also a moving target. As aerosol emissions fell in North America and Europe, the masking cooled less. Greenhouse forcing stood out. Greenland's melt accelerated. The same models that once downplayed abrupt change improved their ocean physics and revealed sharper thresholds. High-resolution experiments that finally captured eddies and narrow overflows produced collapses faster once pushed past a point. The field's own evolution looked like a contradiction from the outside. Inside, it was a course correction. Better eyes, clearer picture. Communication lagged that correction. Scientists hedged, as they should, but the qualifiers piled up. Likely, unlikely, low confidence, medium confidence. The public heard uncertain and filled the space with either doom or dismissal. Meanwhile, early warning statistics matured. Concepts like critical slowing down, rising autocorrelation and variance near a tipping point, moved from theory to application on AMOC-sensitive fingerprints. New, physics-based indicators emerged, like the freshwater transport minimum at the southern Atlantic boundary. That's not an opinion, it's a budget. But folding those advances into policy briefs takes years we didn't spend. One more blind spot: separation of silos. Cryosphere teams track Greenland's melt. Atmospheric scientists track jets and blocks. Oceanographers track salinity and stratification. Each group warned of stress in their lane. Few venues pulled the lines. Together for mayors, farmers, or grid operators in time to matter. You saw record melt, unusual jet, cold blob, and separate stories. The shared cause, the weakening conveyor, stayed backstage. Why bring this up now? Because underestimation is itself a risk factor. If you think the threshold sits in 2150, you defer upgrades, you design for wrong winters, you underprice flood, you skip the moorings that would catch the bend. If you wait for perfect measurement of a system that by definition withholds certainty as it approaches a cliff, you'll meet certainty on the way down. Course correction means three things: upgrade the models to resolve the sinks and eddies, expand the observing system where sinking lives, and fix the story we tell so unlikely doesn't paper over non-linear. This isn't an indictment, it's an audit. The science tightened, the signals strengthened,
The risk window moved into our lives. Now the question that threads through Anna's fjord, Tom's field, Miriama's seed trunk, and Teresa's basement is simple. What do we do with a warning that finally speaks plainly? The world after a flip. New normal or rolling crisis. After the flip, the map doesn't redraw overnight, but the rules do. The AMOC settles into a weaker mode and holds there until the planetary heat load drops far below where the switch flipped. That's a regime shift, not a bad season. Europe learns winters that sit colder, stormier, and more blocked are now the baseline. The tropics live with an ITCZ, a notch south, and the monsoon belt's heartbeat turns irregular. Markets and governments try to smooth it out. Some succeed for a while, many don't. Trade patterns bend around the new climate. Refrigerated shipping leans away from storm corridors that stall too often. Atlantic crossings take slower winter routes. Grain flows pivot. Northern Europe imports more winter calories and exports fewer, while higher latitude farms double down on cold hardy cereals, oilseeds, and indoor greens. Southern supply chains that relied on predictable dry seasons find those seasons mutating. Insurers and lenders raise rates or back out. The cheapest path becomes the most brittle. Redundancy becomes a business model. There are winners in this adjustment. Regions just south of the shifted rain belt catch more reliable moisture and invest in storage, canals, and floodplains that turn bursts into buffers. Ports that sit slightly higher or tucked behind natural barriers capture traffic from neighbors that flood too often. Countries that built storage-heavy power grids with heat networks and interseasonal thermal stores discover they can sell stability. Seed companies that bet early on cold and disease tolerance for temperate crops and drought tolerance for tropical staples expand markets as demand spikes. But the losers are numerous. Low-lying coastal cities face chronic flooding that outpaces budgets. Rural districts with thin tax bases can't keep roads and drainage in repair under clustered storms and freezes. Fisheries co-ops fail when stocks shift faster than governance. Food importing nations pay more for calories when two breadbaskets stumble at once. The cost of capital climbs where climate risk becomes a headline. Migration grows less like a wave and more like a tide that never quite retreats. Families don't pack cities all at once. They peel away year after year from river deltas that salt farm belts that freeze wet and coastlines that flood without storms. Governance gets a stress test in slow motion. Schools absorb new students with different mother tongues, clinics add patients with no records, housing markets split between dry ground and everything else. Some towns plan and welcome, others lock doors and harden rhetoric. Technology answers where it can. Power systems shift to storage, you can count in days and weeks. Heat batteries for district networks, hydrogen and ammonia for industry, pumped hydro that uses caverns and quarries. Buildings get smarter and simpler. Thicker walls, fewer leaks, mechanical ventilation that sips energy and filters smoke from fires in a drier Amazon fringe. Farms layer sensors with old wisdom, drainage and contouring return, alongside variable rate seeders that chase narrower planting windows. Desalination creeps inland along rail lines and canals to feed cities whose reservoirs miss their cues. Culturally, weather starts to mean something else. People talk about infrastructure weather, whether the grid can ride a 7-day freeze, whether the pumps can move rain against a high tide, whether the roads survive a thaw. Forecasts come with system notes, cold load probability, surge clearance hours, storage state of charge, local news features, salinity maps, and floodgate schedules next to school closings. Community groups keep go bags for neighbors and generator cords that reach across hallways. Meanwhile, the ocean keeps bookkeeping. The weak overturning shuffles heat downward and spreads it. The subpolar. Atlantic stays cooler at the surface, but the global ocean continues to warm. Sea levels step up in places the AMOC once held down dynamically. Coral reefs that survived heat waves stumble on longer marine heat spells in the subtropics. The Amazon teeters if the dry season stretches too far. If the south gets wetter with odd timing, parts rebound while others brown. Cascades threaten ice melts faster because soot and heat linger. The AMOC stays low. Rainfall bands keep sliding. Forests that once trapped carbon release it. Not every bad curve steepens. Some cities make smart choices early, move critical gear upstairs, elevate a feeder road, retire riverside parcels into parks that flood by design. Some regions coordinate grain reserves and avoid panicked export bans. Some fisheries renegotiate quotas dynamically and share data fast enough to avoid crashes. The countries that thread these steps together stabilize more than their own borders. They become anchors for neighbors. Bring it back to the original promise. Warning is only useful if it changes choices. The AMOC's flip isn't an apocalypse switch. It's a force multiplier for risks already in motion. The difference between a rolling crisis and a new normal is preparation that meets physics. The conveyor won't bargain. It will respond to less heat and less melt. So will the world we build in its wake. Resolution and meaning. A system we counted on to stay steady is leaning into a new state within our lifetimes, and the odds don't wait for perfect proof. If you want the next piece, how jet streams lock heat domes and coal blocks, watch the episode queued up now. Subscribe for more of the Earth's hidden machinery, and keep an eye on the tripwires, salinity, sea level gradients, deep convection. When they move, you'll hear it here first.